You may have noticed that in Bellman-Ford's algorithm, we relax edges in any arbitrary order. But if we had a directed graph which is acyclic, we would be able to relax edges in a specific order so that we only have to relax an edge once as we encounter it. Remember that if a graph has no cycles, and it's a digraph, so this is a DAG for short, that it has a topological order, which we can find in total linear time using a depth first search. So a topological order is one in which if we have a directed edge from vertex A to vertex B, then in this topological order, vertex A occurs before B. So this is just a labeling to every vertex from 1 to n so that we satisfy this condition. If there's an edge from A to B, then vertex A is labeled earlier, occurs earlier in this topological order than vertex B. And if we do this, then this gives us exactly the order in which we should relax edges. For every vertex along a topological order, we'll relax the outgoing edges from that vertex. And the idea is that if we have in a DAG a directed path from one vertex to another vertex, we can guarantee if we relax edges along a topological order that because there's an edge from here to here, that essentially that we'll correctly set the distance label for this vertex because the existence of this edge means that if we processed edges along a topological order, then we would have, since this edge exists, we would have already processed this earlier vertex. And since this edge exists, we would have processed along that order this earlier vertex. So then we can find a shortest path tree rooted at some set starting vertex S, find a shortest path from S to all other vertices, and the distance from S to all other vertices in total linear time, in big O of n plus m. Again, n is number of vertices, m is number of edges. And we use the same labeling scheme. So we assign a distance label of 0 to that starting vertex S and infinity to everyone else, and this will be improved as we go along. First step, we do a topological sort of vertices. So this is accomplished with the depth first search. We assign vertices a label from 1 to n. And then along that order, for each vertex along a topological order, relax all outgoing edges. So in that edge relaxation step, we check to see from vertex U, which has an edge, to vertex Z, if we can update Z's distance label by using U as an intermediate vertex. So the new cost to get to Z if we were to follow this path would be however much it costs to get to U, which is U's distance label, plus the weight of this edge. Okay, since we only relax each edge exactly once, the total runtime of this is big O of n plus m. So let's see how this would work on an example graph. So here we have a similar graph to what we had before, but now some edges are adjusted so that we have no directed cycles. So this is a directed acyclic graph. We know that we would be able to use this type of algorithm on this directed graph because it is acyclic. And we can use depth first search to determine, can we find a topological order? If one exists, then this is definitely a DAG. Now, this DAG-based algorithm will work on any DAG, whether it has positive or negative edge weights as well. Okay, so our first step is to assign a distance label. If we want to find all shortest paths from A to all other vertices, we'll assign A a distance label of 0, and everyone else will get a distance label of infinity. And let's do a topological order of this. So very quickly we can identify which vertices have no outgoing edges, and since we've got 1, 2, 3, 4, 5, 6 vertices, we'll start with label 6. So I'm going to show just in a box here the label to this vertex along a topological order. So we'll label this one 6, this one 5. Once we remove those ones, those two vertices, then the only vertices that have no outgoing edges would be B and D. So we could label D as 4. And again, this isn't unique. We could have a different topological order, which is still valid. We'll label B as 3. This isn't a distance label, this is its topological order. And A is the first one. Okay, so in this order, so we'll process A, then C, then B, then D, then F, then E. So we'll relax all edges outgoing from A first, because A was the first vertex in that topological order. So let's process this edge, relax this edge. We find that along that edge, we can get to B now in 8 steps rather than infinity steps. From A to C, we can get to C now for a total of -2. And from A to D, we can now get to D in a total of 4, cost of 4. Okay, now we've moved to vertex C, which was the second vertex in this ordering, and relax all outgoing edges. So from C to B, we can get to C in 2 steps, in -2 steps, plus an additional 7 gives us a total of 5, and this is better than what we had before. So just like we did with the other algorithms, we can indicate whether we used some edge or we didn't use some edge. When we relax the edge from C to E, we find that we can get to E in a total of -2 plus 3 gives us 1. This is better than what we had before. And relaxing the edge from C to D gives us that we can get to D now in -2 plus 1 gives us -1. And this is better than the previous way we had of getting to D. And the edge from C to F, we can get to C in -2 plus 9 gives us a total of 7. Now that all edges have been relaxed from the second vertex in this order, we move now to the third vertex in this order, which is B, and relax all outgoing edges. And there's only one. This gives us, we can get to B in, let's say, cost of 5. -5 gives us 0. And this is better than what we had before. There are no other incident edges from the third vertex in this topological order, so we move to the fourth vertex in this topological order. And when this edge is relaxed, we find that we can get to D in -1 plus 5 gives us a total of 4, and this is better than what the previous edge gave. Now that the fourth vertex has been processed along the topological order, we move to the fifth one. It has no outgoing edges. We move to the sixth one. It has no outgoing edges. So we are finished. Now we found that the shortest path from A to B has length 5. Shortest path from A to E, this costs 0. Shortest path from A to C costs -2. From A to F costs 4. And from A to D costs -1.